In lesson 95, we are going to take a look at variance and standard deviation of random variables. In year 1, you learned that the measurements of variance and standard deviations in statistics deal with the spread, so how consistent or inconsistent a set of values are. Okay, and so here we're going to consider a set of discrete random variables x listed as x1, x2, ... all the way to xn. And we'll assume that each variable has a corresponding probability of p1, p2, pn. Okay, and using the variance formula, you can review this from last year's notes or also from the formula booklet. We know that variance takes on the symbol sigma squared, so it's the square of standard deviation, as being the sum of how frequent, so fi, the deviations occur. So fi multiplied by xi minus mu being the mean, okay, of your data set, squared and then over n. Okay, so it's the root mean square sum if we are referring to the standard deviation. Then here we can simplify this by first considering fi over n as being one group. So let me rewrite this. Xi minus mu squared and then multiply by fi over n. So if you think carefully about fi over n, it really represents the frequency of, a certain data point, or in this case, the square of a deviation occurring over the total number of data points that we have. In other words, it really is the probability, right, of the square of the deviation. So I'm going to rewrite that as pi. Okay. So what format do we see here? If I multiply probability by x in the last lesson, I get the expected value. So in this case, I can rewrite this sigma expression as the expected value, E of the square of the deviations, xi minus mu. And don't forget, mu also stands for the mean of a probability distribution here. So mu is actually equal to E of x, the expected value. Okay? So now using this formula, we can now calculate the variance of a probability distribution. Example 1. Consider the random variable x with probability distribution shown here. Find E of x and then the variance of x. We will begin by finding E of x, or mu, which is the sum of x times probability of x equals each x. Okay, so here we have 1 times 0.2 plus 2 times 0.2 plus, well, because all the probabilities here are 0.2, I can easily factor that out. 1 plus 2 plus 3 plus 4 plus 5. So what does that give me? 6, 12, 15 times 0.2, 3. Okay. And now I have the value of mu. I can now calculate variance of x using the formula that I have earlier, which is the sum of xi minus mu squared times pi. Okay. Well, that means I actually need to make use of the value I just calculated as mu. And p of I is just 0.2 throughout, so I can actually set it aside. And then here, for each value of x, this column here, I need to subtract 3, which is the mu value, and then square that, okay? What you could do is you can add a new row, okay, in the table. if it makes it easier. So this is mu value. So 1 minus 3, negative 2 squared. Okay, 2 minus 3, negative 1 squared, 0 squared, 4 minus 3, 5 minus 3. So all squared. So taking those numbers, I have 4 plus 1 plus 0 plus 1 plus 4 again. So this is 10 times 0.2, which is 2. On the next page, prove the following properties of e of x, the expected value of the random variable x. So first of all, we want to figure out whether e of k is actually k for any constant k. Okay, so I'm going to start by writing out the definition of the expected value of e of k. So here we have e of k equal to the sum of k pi, right? Because k is a constant, I can factor it out. So k times the sum of all probabilities from 1 to the very last value of x. But what I know is that this part here is equal to the total probability of a probability distribution. So what should that equal to? That should equal to 1, because sum of all probabilities in a probability distribution. Okay, as a result, this is equal to k, and we have proven the statement. B, let's prove that e of kx is equal to k times e of x for any constant k. So I'm going to go from left to right. So e of kx is the sum from I equals to 1 to n of kx p of I. Okay, again, I can actually pull out anything that doesn't involve x in it in the summation calculation, which is k. And then here I have n, I equals to 1, x pi. And I hope you recognize that this is the definition of expected value. As a result, I have k times e of x. Okay. C, we have e of the sum of two functions, g and h, equals to the individual expected value added together. Okay, so what have we got here? So I have to write out the definition first, which is g of x plus h of x times p of I, right? But using distributive property, I can have g of x times pi, whoops, I should write it smaller, plus h of x times pi. Okay, and this is all one group, but the summation properties allow me to separate the sum of the two terms into the sum of g of x pi plus the sum of h of x pi. So you can't skip these steps because you're actually applying different properties in each step in your proof. But of course, in the end, I recognize that the first term is the expectation of g of x plus the second term, which is the expectation of h of x. Okay, proven. So now, we will use the above properties of e of x to find an alternative formula for the variance of x. So we can start by looking at the variance formula, which is the sum of the square of the deviations times pi. Okay, and mu is equal to e at x, the expectation. What we have here, we can write this as e of x minus mu squared. And now I can expand the binomial. I get x squared minus 2x mu plus mu squared And then because the above property showed me that if I have an expectation of a polynomial, I can split up the polynomial and write this as the expectations of each term, okay? E times 2x mu plus E of mu squared, like that, okay? And the middle term here, I can actually split it up further because this is 2 mu times E of x, because mu is just the expectation itself, which is a constant, so I can pull it out using the property in B. Okay, so using the property in B here, plus E mu squared. Okay, and now I can sub in mu as any E of x. Okay, and then what have I got here? This gives me variance of x equal to E of x squared minus 2 mu squared plus mu squared. Okay, and so this is E of x squared minus mu squared. But then I will back substitute mu squared using E of x. Okay, so don't mix up the first and the second term here, because the first term in this alternative formula for variance, we're evaluating the expectation using the square of x. But in the second term in this formula, we are actually taking the square of the calculated expectation. Okay, so it's not showing up properly here. So let me fill it back. Okay, and of course, don't forget that the relationship between standard deviation and variance is sigma and sigma square. So just square root the result, and there you go. You get the standard deviation. In the next part of this lesson, we're going to explore the properties of ax plus b, so any linear transformations, okay, of a data set. So going back to the probability distribution we had from example 1, shown in the table here, I'm also going to include the expectation that we have calculated, which is 3, and the variance that we have calculated 2, okay? In example 2, we're going to consider a different random variable, but we're going to kind of relate the two examples, okay? So this new random variable, we're going to call it y. It is calculated from multiplying x by 2 plus 3, okay? So here. So starting from x equals to 1, now we have 2 times 1 plus 3, 5. 2 times 2 plus 3, 7. 2 times 3 plus 3, 9, 11, and 13. All right. And we're going to calculate the expected value of y. I know that E of y will be, well, since all the probabilities are 0.2, I can use a shortcut, factor it out from each term, and then multiply by 5 plus 7 plus 9 plus 11 plus 13, which is 9. Okay. Next, I'm going to find the variance of y. Now, this time I'm going to use the alternate formula, which says E of y squared minus E of y all squared. Okay? So E of y squared is 0.2 times the square of each one of those y values added together. So again, factor out 0.2. I have 5 squared plus 7 squared plus 9 squared plus 11 squared plus 13 squared. Okay, so you can see what I actually substituted. Minus, we already calculated E of y as 9, so 9 squared. Using your calculator, this works out to 8. All right. So hold your thoughts there, but you know we will be comparing this to e of x, the original, which is 3, and var x, which is 2 later, okay? Okay, so now we're going to repeat part A for another random variable z. Z is negative 3x plus 5. Okay, so I think we're starting from x equals to 1 from the original chart. And then so negative 3 times 1, negative 3 plus 5 is 2. Negative 3 times 2, negative 6 plus 5 is negative 1. Okay, so keep going. I get negative 4, negative 7, negative 10. Let's calculate e of z. Let me use blue. Okay, once again, 0.2 for uniform distribution. It's easy. We can factor it out. 2 minus 1 minus 4 minus 7 minus 10. And this works out to negative 4. Okay, the variance of z can be calculated from e of z squared minus e of z squared. Okay, so e of z squared is 0.2 times 4 plus 1 plus 16 plus 49 plus 100 minus negative 4 squared. Okay, using calculator, I got 18. So once again, let me list out e of x, which was 3, and variance of x, which was 2. So in part C, state the relationship between 1, e of x and e of ax plus b, 2, variance of x and var of ax plus b, as well as 3, sigma x versus sigma ax plus b. I know in the chart it already listed it. In your handout, you think, oh, I just have to copy it. But let's try to understand what happened here, okay? Now, if you remember last year, we had this lesson where I have put a bunch of Totoros on it. Those cartoon characters that are lined up, if you remember that. Okay, so that lesson, we talked about, well, what if I apply a linear transformation to a data set? What happens to the mean and standard deviation and variance and so on, right? So here, e of x, expected value in a probability distribution. This is mean, right? This is the measure of central tendency. Consider the values of your variables y and z when you compare them to the values of x. Well, when I apply ax plus b, both a and b affects the new values of these new variables, which means that, the value of the mean will also get, stretched by a so-called stretch and also shifted by b. As a result, e of ax plus b must be a times the original e of x plus b. Now, what about variance? Variance is the measurement of spread. So think of if I have, 5 objects lined up and I just shift them over, every single one over by b steps, okay? 5 steps, 7 steps, I don't care. Will the relative distance between these different objects change when I shift them? They won't change, right? But if I say multiply the distance or multiply the values of these numbers, then the gap between them will change. As a result, the spread is only affected by the stretch factor, which is a. But we have to think about variance one step further, because variance, as we know, is the sum of frequency times x minus mu squared over n. So we're not just multiplying frequency by x, but x squared. In other words, any changes that I make to x needs to be squared as well. So that's why there is a squared in this formula, okay? And then for sigma, which is standard deviation, sigma is the square root of variance. So now in variance, we square the number and now we square root the number back. So that means standard deviation will only be affected by A. But we want to make sure when we state standard deviation, it's a positive value. So that's why we have to include the absolute value symbol here. Okay?